Let's dive into something that sounds a little crazy at first. We're going to explore this mind-bending connection between two worlds you'd think have nothing to do with each other: the super abstract philosophical world of formal logic and the very practical, hands-on world of computer programming. What if I told you that deep down, at their very core, they're actually the exact same thing? So let's just start with this wild thought. What if that step-by-step argument a mathematician scribbles down to prove a theorem, what if it's not just an argument? What if, under the hood, it's actually a piece of software, an algorithm just waiting to be executed? This isn't just some fun little thought experiment. It turns out to be a really deep, fundamental truth about how logic and computation are related. And of course, it has a name. It's called the Curry-Howard isomorphism. Now, isomorphism is a fancy word, but all it really means is that there's a perfect one-to-one mapping. For every proof you can write in a certain kind of logic, there is a program that matches it perfectly in a certain kind of programming language. And it goes the other way, too. They are literally two sides of the same coin. Okay, so here's the simplest way to think about it. In programming, right, you have data types, things like a number or a string of text. Well, under this whole isomorphism thing, a logical formula, like if A is true, then B is true, that acts like a data type. And the proof? The proof is the actual program, the algorithm that gives you a value of that type. It's the code that actually fulfills the promise of the logical statement. Okay, I know what you're thinking. How can a proof, which is all about truth and reasoning, possibly be the same thing as a program, which is about, doing calculations? Well, it's because they can both be written in the same secret language. And that language is the lambda calculus. Now, don't let the name scare you. As our source material brilliantly puts it, you can just think of lambda terms as a special notation for proofs. It's a way to write down the steps of a logical argument so that it doesn't just look like code, it actually acts like it. This really is the perfect analogy. Lambda calculus is like the shared DNA. It's the underlying genetic code that allows an idea from pure logic to also be a process that you can run on a computer. So we have this shared language, and just like in programming, where you have different styles, object-oriented, functional, logicians have different systems for building their proofs. And it turns out the shared DNA works in more than just one of them. So the two big styles our source material talks about are natural deduction and sequent calculus. You can think of them as just two different ways of getting to the same answer. One feels a bit more intuitive, kind of like how we naturally think, and the other is way more rigid and symbolic. But here's the kicker. It doesn't matter which style you use. In both systems, you can use these lambda terms to write down the proofs. It just shows how deep this whole connection really goes. All right, this is the moment. This is where it all really clicks into place. We've been talking about how proofs and programs can look the same when they're just sitting there on the page, but now we're going to see what happens when we put them in motion. This is the real magic. This is the absolute core of the whole idea. When a logician takes a long, complicated, roundabout proof and starts cleaning it up, removing unnecessary steps to make it more elegant, they are, whether they realize it or not, performing an act of computation. They are literally running the program. And these two processes even have different names in their own fields, but they are the exact same action. In the world of logic, simplifying a proof is called cut elimination. In the world of lambda calculus, the most basic step of a program actually executing is called beta reduction. They're perfect mirrors of each other. So let's just walk through it real quick. You start with a complex proof, one that has a redundant step. That's called a cut. Then you apply the process of cut elimination, which is identical to the beta reduction step in computation. You're literally running the proof. And what do you get at the end? A simple, direct, cut-free proof, which is also the program's final answer, or what's known as its normal form. And hey, don't just take my word for it. The source material spells it out perfectly. It says cut reduction in proofs directly corresponds to beta reduction in lambda terms. It's one single process with two different names connecting two entirely different worlds. It's just incredible. So we've laid out this absolutely amazing deep connection. But okay, beyond being a really cool piece of theory, does this actually matter in the real world? Does it have consequences? Oh yeah, a big one. This is so much more than just a theoretical curiosity.
The implications here are absolutely profound, and they've totally shaped the technology that we all use every single day.
So first off, it guarantees logical systems are consistent. If every proof can be simplified to a direct answer, it means you can never end up in a situation where you prove something is both true and false. No contradictions. Second, and this is the one that's a huge deal, it lets us automatically get working code directly from a proof. Just imagine that for a second. You prove, mathematically, that your sorting algorithm has to be correct. And from that very proof, a computer generates the actual bug-free program for you. I mean, that's the holy grail of software development. And finally, this whole idea is the foundation for the type systems in modern programming languages. The very things that catch countless bugs in our code before we even try to run it.
So in the end, we've seen that this very human act of logical reasoning is in fact a computational process. And that just makes you wonder, right? If a mathematical proof is just a program waiting to be run, what other complex structures in our world, maybe even biological processes or social systems, are also secretly a form of computation, just waiting for us to figure out their code?